what I thought we could do would be, let's see now. I could, I think you guys have, I'm going to talk to just, well, the syllabus, you guys already got my syllabus and kind of seen some of the things about it. So, I love having it referred to on the screen. But anyway, I'll even kind of defer to, I think next time, talking a little bit about any of the details in the syllabus, and any questions people would have, you know, because we'll have, well, I think 3 tests, then we'll have a research project, which is kind of like homework, it's just kind of ongoing. So one thing actually I would like to do is to get some feedback on what kind of data might be useful for our research project. So anyway, we'll have these tests, we'll have, the tests kind of are more econometric theory, because this class is kind of looking at the rigorous fundamental foundations of methods you might already know how to use, like multiple regression. How many people have run a multiple regression on stage?
Excuse me, bro. Says you should let Wafa in on the Zoom. Wafa.
Yeah?
You should let her in on the Zoom.
Oh, thank you. Oh, she texted. Oh, so thank you very much. Thank you. Great. Thanks so much. Well, and at least this part I think is working. Hopefully the sound is working. And so it's good. Yes. So let me actually, I'm going to turn off that screen so I can write here on this part. Oh, thank you, Gary. On this part of the board. Actually, a double press. It's a secret thing that now you know. Don't tell anyone else. It's a double quick press on the button that does for the front.
The power?
Yeah. Awesome, thank you. So, let's see now. Data for the project. So my idea of a project for this semester is actually just the same project that everybody will do, but at the end of the semester, I'll have just maybe kind of randomly pick some questions that each student will present. So during our finals week, we'll just have, you know, everybody will have maybe like 15 minutes or 20 minutes, just talk about the problems they worked on and what solutions they found. So that's just kind of more practice. You know, and if you're working on those problems during the semester and you have some questions, you know, that's fine too. So I'm our teaching assistant, he's not, and Yaga will also be available. Oh,
Joshi,
2 more people
Joshi,
are waiting.
right?
Admin, I have to get better at, oh, sorry. Oh, Joshi, right? See, that's embarrassing. See? That's terrible. Joshi is here now, thank you. And what's worse was I wasn't letting everybody in on time, because I've never run one of these Zoom sessions. What a disaster. But even with all these disasters, I think we'll make a bit of progress. So, Joshi and myself would be very happy to assist if you're stuck on one of your assigned project questions. We'll make sure that you're able to pursue those questions and work on those during the semester. One thing, though, is that we would want a data set that's exciting. Because what I'm planning to do is, I emailed you some notes for our first week of class, actually, it's a few pages. And they have questions at the end, and we're going to get to a few of those questions today on the simple regression model. But I also want to have at least one question at the end of each note is kind of an application question, so a project question. And so we'll have the same project data we'll just work on during the semester. So, and I'll figure out, but I figured instead of me just choosing the project data, I thought I could ask you all, what are your interests? And, you know, could we pick a project data set that you think might be interesting? And then I can just, you know, design problems from that data set.
I have a data set. A survey that I created last semester with students at the college with about 200 surveys. So if you wanted to use that, it asks questions about health, students' health, income, and their all their demographics, and a couple of questions about their usage with social media.
Let's see. So SIU student data.
We can't say it's SIU student data, but
Oh. Mm-hmm.
that's one of our, you know. guidelines. We just say it's student data. Student data.
On health,
Health,
different demographics.
mental and physical.
Mm-hmm. And then, let's see, what would be the last thing, kind of things you were mentioning in there?
Social media usage.
Social media usage.
All the
Oh.
questions that could go with social media. And this was done under Dr. Friesen, but she's from the London School of Economics.
Wow.
So she studies here. She's in the School of Journalism. Karen, her last name is Karen, first name.
Hmm.
Can't remember.
No worries. London School of Economics is very famous. This sounds like a very interesting possible example of some data that one could look at, and it's something that you hear.
This is kind of her field of study,
Mm-hmm.
and it's breaking right now.
Terrific. Well, that would be a very, very wonderful example. So, Danny here has already suggested something that just sounds like it'd be super, super terrific for us to look at this semester. Are there other possible examples of data that you're excited about, you might have worked with, or you might be interested in?
I'm interested in financial technology.
Financial engineering?
Financial technology, fintech.
Financial technology. Awesome. I had to get a pen. I don't think that's going to work too well. Maybe on screen I might have to run and.
Okay.
You think? Thank you.
You might not have one.
I'm not. I think we might have.
Yeah, and
It's a little faint there. Actually, let's see. How are we doing? I think my head was chopped off earlier, but this is probably, we'll be doing so much better next time when I'll have my computer showing on screen to these students in class. Let's see. I'm just looking into the screen. Hello, that's the info, Wafa, Haya, and Joshi. You guys can hear me okay, I guess. If you can't, just let me know. I don't, oh good, the thumbs up is there. Excellent. And can you kind of see the board okay? It wasn't really the intended design this morning. I'm getting darker markers, so hopefully that might help a little. Hopefully when I'm talking, it kind of, oh thank you so much. You can kind of tell what's going on. I'll just write a little darker.
And when you say financial technology, do you include new services like Robinhood trading?
I'm not familiar with the ecosystem in the U.S. So
Or
what does
tra-
Robinhood do?
Like trading platforms.
Oh yeah.
Okay.
And what would be maybe an example of data that we might get that would be related to financial technology that we might want to analyze?
So there are lots of data that we can create and utilize from the financial technology ecosystem. Like for example, in Southeast Asia particularly, there were a lot of investment going on. SoftBank invested on some financial technology startup in Indonesia, India, Singapore, and Philippines, Southeast Asia, and South Asia countries. And there are also, what's interesting is like this. So one investor could invest to many startup entities, and then we can actually try to map their investment, so we can actually predict if there is going to be a merger what startup will merger.
Mm-hmm.
Because now in Indonesia there are two big players on payment system. It's called OVO and Dana. So OVO is funded by one conglomerate in Indonesia called Lipo Group, and another is from it's called Amtech Group, and they're going to be merger. And we know that we can actually predict that by, you know, like drawing the network of which investor invests to which company, something like that.
Mm-hmm. Very, very interesting.
Now, are these payment systems like Wirecard?
No, it's like WeChat Pay.
Mhm.
WeChat, okay.
Yeah, so you're using your phone number to send and receive money.
You know, I can't believe what happened with Wirecard.
Oh, Wirecard.
The payment system, like they're like the payment system in Europe.
Mm-hmm.
You know what happened, right? The CEO lied, or they lied about having a lot of billions of dollars on the financial sheets.
dear.
It's the Enron of this year.
Mm-hmm.
And now we're actually having another Enron situation, rolling blackouts in California after
Well,
20 years again.
Yeah, that's true. The heat, global warming. Oh,
Is
goodness.
this an Enron situation, you think?
I'm not completely sure, but what an interesting additional subject here possibly for a data set that we could perhaps look at during this semester. Now, by the way, next semester, for those taking Econometric 3, you'll be doing your own project too, your own data. So we're here just kind of pick something we can get our hands on and work with as an example. This semester, here are a couple of different possibilities. Any other data set sounds like something you'd be interested to work with, explore, something?
I'd like to work with macro data from World Bank.
Macro data, World Bank. There's definitely a big bunch of freely available too, macroeconomic data from the World Bank where you can explore, of course, a great many different intriguing and interesting themes and topics. So, now could conceivably even be, I wouldn't necessarily have just one data set during the whole semester. I could have a project where maybe we could have a, one data set to start with, and then, we could definitely put in one other data set or two. Certainly wouldn't be still the same spirit of the course, just have a couple other data sets as well. Maybe that might be possible. For example, let's see, I guess Denny has this first data set already. Maybe what we could consider is we could maybe start with a simple regression even with that on Thursday. And then maybe we can plan perhaps to have, especially if you guys maybe have some particular variables in mind, maybe a particular source of data where we could get a data set with the fintech and the macro data, and then we could perhaps use those as we move along at some point too in the semester. So that could definitely work. So anyway, a thought about data I wanted to gather some info from you so that I can then start designing those parts of our lecture notes where I'll actually have those data sets mentioned. And so, again, if you can get me, email me the...
I've already sent it to Featree. I can just forward you the email. Remember I sent it to you last semester?
Yeah.
It's easy. I can just search her. It's right there. I can forward you the email from Featree.
Forward to seeing it, then I can sort of set up so we can do our
Wonderful.
little lab.
That'd be so cool.
Next time. Terrific.
And one more thing about the macro data, I think that's a great idea. I would love to just kind of go through all the variables and find out which ones are pro and acyclical.
Yes.
To see which ones are, positively and negatively related with the state of the economy.
That's definitely possible too, and interesting. Yes, for sure. Terrific.
Get a better understanding. When you look at those numbers and you say, oh, everything we learned, it makes sense. It's coming together like a puzzle.
Yes. Now, let's see. So next time I'll kind of like have everything up and running, so I'll even peek through the syllabus and see if there's anything I'm obviously missing. But we mentioned the project, we've got our test that we'll be taking. Oh, and I guess we're taking the test, since I won't require people to be here. And my ideal was everybody would kind of take the test online, so you wouldn't have to have physical tests to work with, and it would be safer for anybody grading too, if you're a grader, to be assisting in grading. So for that, we can talk more about that later, but hopefully if you all have like a cell phone that has scanning on it, because actually, and that's, if you can scan the PDF, that was great. Taking pictures of test pages is a nightmare for your grader. So it was okay for me last spring when I tried it, but wow, if you have more than a few students, having to put them in order, flip them upside down, stuff is really a bit of a challenge. So yeah, if we can just get all trained, and I'll do that before, just make sure we'll know how to just get that app, scan the PDF, and we can go ahead and take our test and our retreat test in our regular class period, but, we can just be doing them, you can all figure out how this best works, but I can just make sure you have the PDF, and then if you can print. You guys have a printer. If you don't have a printer, maybe we can see how's the best way to do that. You don't have to type the test. Is there a better, you can use a stylus. Actually works pretty well. I'm going to be using a stylus during the semester if you have a touchscreen, like a laptop, but many people may not. So I'll see what the students have in terms of resources. Do they have? I can get a print copy probably. Well, I can make print copies. I just want to reduce the extent to which we have to touch, other things, paper. So we can talk about what is the best way to do taking our tests. That was kind of the solution I thought of. It would, kind of work, but I'll just see what works in terms of your resources and how we'll make that best work. I thought I would just mention that, and then we'll kind of return to, you can maybe give it some thought too, and we'll turn to that next time. And then what I wanted to be able to do is kind of get into our first topic, write down our model, and look at a few questions about our econometrics. So let me actually try to go ahead and do that a little bit for our class today, and then we'll carry on next time. Do we have any other questions? This is a special semester. This is not your first class this semester, so maybe you're already kind of finding your way. This is my first class to teach in class this semester. Do you have any other questions though? And let me just...
Are you teaching your undergraduate classes online, or?
I have one online. Actually, it's just a traditionally online class. But then I have one class that's like this, but more students in a big classroom. But I'm going to be doing the Zoom as well. Hopefully, that classroom, the technology will all be working with the coding. And does anyone, Basim, Hope, Wafa, or Aya, does anyone have any questions? If you do, hopefully, I can be able to hear and be happy to answer that. Board is not that much clear. I see that comment. Okay, thanks. I'm sorry. Yeah, so next time I'll be writing on my screen, so it should be very clear. Yeah, I'm sorry if the board is a little hard to see with my webcam. I'll try to write big. I'll write a few things, but there also will be in the notes. So the main thing. So that we will. I'll not tax your eyes too much by looking at the board. Another reason I like writing on my screen this semester is this chalkboard, whiteboard. Was no one writing last time on the board yesterday?
No. One question. Which do you prefer, a Logit or a Probit model in your own research?
Oh, well, I think both are wonderful. And I don't know exactly a logical way to choose between them. Probit was has kind of some more classical underpinnings because it's associated with a normal distribution. But really, they also empirically give very, very similar fits when you fit these two different Probit and Logit models. And we'll explore them later in the semester, as well as a Tobit model. So very often there's not a whole lot of empirical difference between your applications of Probit and Logit models. And kind of theoretically, there's no particular reason to choose one over the other. I like Probit because, I like the sound of it, but then logits are somehow associated with an extension of them as artificial neural networks, which is a super cool modern topic. Who couldn't like that? So I like them both, I think. So let's see. Now let me see if I can go back to my notes so we can do a little econometrics here. We already talked a bit about some data and other things. But our first topic really is, I'm just afraid if I move over there, there's no chance these guys will see me or hear me perhaps. If this is dark enough, maybe this would work. Actually, the board in the lab is much better, but I think the room is a little bit small there. Simple regression model. Let's write down the simple regression model just as our beginning point of the semester. In the simple regression model, and even though you guys are probably going to have a hard time seeing it, let me just see if I can make it look a little better. So we have y, which is an outcome of interest. So let's see, with Danny's data, I think it's health. It doesn't depend on people's use of social media. Too much social media bad for your health? I wonder. That's just fascinating. He becomes sort of this, there was a book in which I think it was called The Time Machine by H.G. Wells. And this character, the protagonist in The Time Machine, travels into the future, hoping to see an amazing population of enlightened people in utopia. But what does he find? He finds these beautiful people wandering around on the surface of this planet carefree. And then he finds out, though, the way they're able to live is these people, the Eloi, are provided food and a way of life by the Morlocks who live underground. And in exchange, the Morlocks, from time to time, as is necessary, will eat an Eloi because that's how they get their food. Oh! Anyway, very
Same thing happened in the movie with the superheroes I just watched not too long ago. It was one of the Avengers, or the latest Avengers movie.
Yeah. Are we becoming Morlocks because of our excessive use of this technology? Social media turning us into these mere shadows, the people that we might have been, and looking rather sickly and being unhealthy. I have no idea, but wow, that would be interesting. So an example could be health. Economic outcomes can include GDP, money. Money is a great economic outcome to study. Income, wages, GDP, profit, all interesting economic outcomes. But that's not all. If we look at measures of overall economic well-being in the world today, we don't have only GDP. We have something else. It starts with H. H something something. HDI, Human Development Index, or indicator, I think. Index. Human Development Index does not only include the GDP, or wages or income. It includes health. Important. Economics acknowledges the importance of health as a measure of economic well-being. And there's one other component of HDI, which is education. So, traditionally, in our econometrics course 20 or 30 years ago, pretty much, the outcomes of interest really were somehow about wages, income, could be employment levels, output, and those were kind of a core of what economists thought of where the well-being of people in economic terms. But today's economists acknowledge that you can have a lot of money to be sick, and you can also, if you're lacking education, that's also a fundamental kind of poverty, especially for society on the longer term. So anyway, health definitely today is of interest for economists to study, whereas 50 years ago, perhaps they would have thought, well, that's not really for us. But today, certainly, it could be.
One of the data is study habits.
studies habits.
So we could look at your
Well,
academics.
Yeah. Too much studying bad for you? Too little studying and therefore more partying bad for you? I wonder what the relationships are. It sounds very interesting. So in the simple linear regression model, we have alpha plus beta. We can have different notation, but often the simple linear regression model would be like this, where we have y is our dependent variable, health, x is our independent variable, and two, actually kind of implicitly or sort of thinking that you've seen a simple regression model before, and probably even perhaps a multiple regression model. It's not necessary, but indeed I know that probably as undergraduates you may have had the statistics class. And then perhaps some of you already have applied econometrics where we've seen extensions of all these things. So what we're going to do though is kind of revisit a model which many of you perhaps have seen before, but look a little bit more closely at it, look more at the kind of analytics of how things work within the model. And at some point even use matrices, like probability, in ways that probably you haven't seen in other courses. And then we'll move to the multiple regression model where we use even more extensively matrices and other mathematical principles, calculus and matrices to kind of see how things are working. And the hope is you get more power and control over the tools of regression when you have those kinds of foundations and skills. So let's see, dependent variable, independent variable. So we have our dependent variable. We have our independent variable. So what could be study habits, could be social media usage, and then we have the error in our model. We don't like to make errors, but there's no particular reason to think that social media usage is perfectly correlated with health. Many factors affect health. So probably if we were trying to make a prediction of health only using social media, it's not going to be perfect. As a prediction, we're going to have an error. So we then also have some assumptions that would go along with this. So let's see. Well, we also have parameters. So we have alpha and beta. Our parameters, and that's a term that usually is meant to say that we're having some relationship between y and x that holds true, at least on average, across the whole population. So that by alpha and beta, we're thinking of parameters that describe or summarize behavior in the population. Population parameters. So here we have the population intercept. And population slope. Now, let's see. The error itself is probably going to have some properties. We'll have to make some assumptions about this error. Because if we had nothing more to say about the error, really the equation wouldn't really necessarily mean anything, because we could make this equal minus this, and then y would just be 0, for example. So we need to make some kind of assumptions about the errors in order for our regression equation to really mean anything at all. And so let's see. In our notes, the errors are, in the classical version of the model, independent and identically distributed and independent of the x's. So the errors, maybe I'll put errors with an S, I'm going to say are independent and identically distributed. Maybe I'll use this notation. I will use that more, but I'm just shorthanding what's in the notes. Normal, N for normal. And for a normal random variable, sometimes we write N for the normal distribution and 0 for the mean. And then there'll be some variance. And our parameter for the variance is usually sigma squared. So, and I could even put like an E here if I want, for the variance of the error. So IID normal, the errors, and so the errors being like a random sample, when we sample at random from, well, an extremely large, in fact, infinite population. with random sampling, it's often common to assume IID. And we also have to assume, though, in order to kind of have our usual interpretation of this model, that the x's and the errors are independent of each other. And there could be a bunch of different x's and y's and e's, and how many do we get to have here? I think it shows that there are 1, 2, up to n different individuals on. So this will be our sample. So we're kind of saying that within the sample that we observe, there's a relationship between y and x. We're also secretly thinking that the same relationship is holding not only in our sample, but beyond the sample as well, across the whole population. So we're thinking there's a whole population, but for our model, when we write it down, we may just say that it's here applying to our sample so that we can analyze the sample and try to make some conclusions, even though we're actually thinking the same pattern is holding across the whole population as well. So anyway, so we could say that the collection of the x's is independent of the collection of the errors.
And that's what IID is short for?
Let's see, so yes, the first I in IID is independent. And what that means here is that the E1 is independent of E2, E1 is independent of E3, and so on. And in fact, any collection of the E's, if you take part of them, that's independent of the remaining one. So that would be the mutual independence of the errors.
So if it violates this, it's heteroscedastic?
Good question. If the heteroscedasticity, depending on the form, so there are different forms of heteroscedasticity. The simplest one is actually just to say, well, what if some of the observations have bigger errors than others? What if some of them have a variance of 2 and the others have a variance of 1? Well, that would be heteroscedasticity. So that would mean that it is not identically distributed because it's different. You got some with high variance, some with low variance. So that's a way in which IID can be violated by heteroscedasticity if you have different variances and so not identically distributed. It's also possible with conditional heteroscedasticity where the size of the E or the E squared depends on something. Perhaps depends, maybe the E squares are like correlated with each other, even though the E's are not. That's possible. It's possible that you could have, now would that imply, let's see. So there could be a form of something like heteroscedasticity that could be associated with the errors not being independent from each other. In fact, if there's a ARCH, conditional autoregressive conditional heteroscedasticity, where the errors are uncorrelated, but they're not independent of each other, because there's this heteroscedasticity pattern, a conditional heteroscedasticity. So anyway, just means that actually heteroscedasticity is an interesting kind of behavior, where you can have IID not being true, both either because we have not identically distributed, that's the simplest case. And it could also be the case that then it causes the errors to be not independent from each other. So a couple different ways that that could work. And that also kind of shows that, we won't always be able to, we won't always assume IID. Because there are different examples where we could have real data where, the assumption is not necessarily valid. And some of you have already had applied econometrics courses where we've seen, the white corrected standard errors, white tests for heteroscedasticity, and so on. And what we'll do in our semester is also kind of look at more at the, some theoretical underpinnings of that methodology, in part so that we can kind of better explain our research when we're publishing it, because we kind of know more systematically know the analytics behind it. And ideally, we'll be able to use more effectively maybe some of the most recent research tools that harness these principles of heteroscedasticity, but maybe in ways that we didn't see in our applied econometrics course yet. So hopefully we get a little closer to the frontier of the methodologies that are out there by kind of knowing the heavy analytics that's going on. So this, anyway, is our classical regression model. And so it's something that perhaps is familiar to some of you. And what I'd like to see if we can do is work on a few problems that look at this model, though, from the perspective that we'll take in our course, where we'll ask questions about how things work and try to see if we can add some skills to get to questions that probably you haven't seen about this kind of model. And that'll be kind of the starting point for our class. Now, I think I could write down, because we have it in the notes, and by the way, I'll have a class at 10, let's see, check, make sure I'm right here. I have a 10:40, 10:50, no, it's 11. So that means we're scheduled to finish at 10:45. I'll go ahead and see if we can maybe finish it, maybe 5 minutes early, perhaps. Just so I can make sure I can get, because you can see how much technological difficulty I have with this one. This is with undergraduates, and 30 of them, so 20. What I'd like to do is, let me see if I can write down the famous formula for our OLS estimator of the slope of the model, and then start asking just a few questions. In our other courses, we may have assumed things like, well, what's the distribution of the OLS estimator, or various other properties of it. I just say, well, here it is. This is what it is. This is what this is. So in this class, we'll try to be able to show, or prove, or understand why it is kind of more substantially or rigorously why these different things work the way we assumed that they would. So, because what I'll try to do is to keep things within my screen here. I think I'll sneak in over here on the OLS estimator. OLS and so too, what we're thinking of is a straight line relationship between y and x. I can sneak that in. We've got x, we've got y, and then we've got some kind of a straight line. Intercept, the slope, beta, and we have our straight line, alpha plus beta x. And we'd like to know, for the population as a whole, what would be the slope that would best represent the relationship between y and x across the population. And so we have our famous formula, beta hat, which is the sum of, and so I'll be using our Greek letter notation that possibly you've seen before, xi minus x bar, yi minus y bar, over xi minus x bar, quantity squared. So we've got, so we could have perhaps seen this before. There's various different ways of writing the beta hat, our OLS slope. One way is this formula. It's kind of relatively simple. It's got one of some squares. Sum squares upstairs is almost like the sample covariance. If you divided this upstairs by n minus 1, you have the sample covariance between x and y. And downstairs is almost the sample variance of x. In fact, if you divide the downstairs thing by n minus 1, you get a sample variance of x. And that also can help the interpretation of beta hat. But anyhow, this is our OLS estimator beta hat. And we have for alpha hat, the y bar minus beta hat, x bar. And there we have it. So that is then something that some of us may have seen before. Maybe not, right? Let's see. There's a couple other things, but I'm not so sure if we'll quite need those. Let me see if we can work on a few problems that would be related. We actually have 9, 10 different problems I see that I put here that are ways to kind of practice with and the model that we've just seen. I'm going to see if I can get started with those. And these are in the notes, which would be on the screen for you and be working with them. But But let me just mention, the first of the problems that we could work on here is in the simple linear regression model, find the conditional expectation of y given x. So in other words, find the expectation of yi given xi. Find the conditional expectation of y given x in the model. Now usually, once we write down a model like this, we just tell the reader what the conditional expectation is supposed to be. Since we're now in econometrics 2, we can hope that we can actually kind of show or demonstrate what that conditional expectation is. Let's see, I kind of think I remember what it is. How can I prove what that is? I think I can just try to use this relationship and see how far I can get. What if I write the expectation of y given x, and for any given individual I is expectation of, well, I could just write in what is y according to our model. If yi has a formula over here, maybe I could write in and substitute that expression for y that we have in our model and see if something comes out when we find the expectation. So that would be the expectation of alpha plus beta xi plus error given xi. Now this is kind of just throwing into some notation e of something bar something else. But that's shorthand, and we'll use it, and we may have possibly seen similar notation before. Expectation of y, which is the same as the mean value of y, but conditional on the observed value of this other variable x. This conditional expectation must be the expectation of this whole expression here given x, and then we can use some properties of conditional expectation. So that's to kind of assuming that we have somehow seen those, at least properties of mean value. Yeah.
Someone said you should let him in into the Zoom call.
Oh, thank you so much. And you know, by way of introduction, because I even have a spreadsheet with your name, so it's going to put your data interests and so on. I just wasn't able to, but thank you so much. And next time I'll actually go around and everybody sort of, let's see. There. One more person has admitted. Nolan, welcome to the class. Sorry, you were in the waiting room there for a while and I didn't notice.
You want me to post this on YouTube?
Oh,
I could.
that's also possible. You know, I think, hopefully there, yes, another option.
Why
I'd
not?
like more options for technology.
I'll do it.
Sure, thanks.
Yeah.
Let's see, and is that actually even, let me pivot this a little bit, so that, because I don't think you guys could actually see my other part there. So sorry, I was writing on the other board. Now, by the way, this stuff is in the notes, but yes, if Danny, if you'd like to,
I'll do it tonight.
thank you so much, that is perfect. So we're over here on the other board, because I was going to borrow some of that real estate, I think maybe you can see that, or your classmate Dana is actually also videoing it just now. So, one property of conditional expectation is the expectation of a sum of things is the sum of the expectation. That's true of the mean. The mean value of a sum of variables is the sum of the mean values. So we could use that here because alpha, that's supposed to look like an alpha. Alpha is a constant. Beta is a constant. And so x's and e's are variables, but that means that I could write this is expected value of alpha plus expected value of, well, let's see, I should say, take it back, it's true, but I need a condition on the xi. That's supposed to be in there. Expected value of alpha given xi. That would be my first term, and then I have a middle term, expected value of beta xi given xi plus expected value of e given xi. And that 1, 2, 3 parts. And then perhaps we can use some of the additional properties of our model to see what these things would be. Well, one is that alpha is supposed to be a constant. It's not random. So we already know its value because we're assuming that we know the constant. Well, we know that they're constants. And so they don't have any random elements. So expected value of a constant is supposed to be just that constant. So this first term, expected value of alpha given xi, is just the same as alpha. The middle term is expected value of beta xi given xi. Well, we know xi. So since we know xi, we know this xi part of beta xi. And beta itself is a constant. And in fact, if the constant comes outside of the expectation, we can do that because it's a constant. So anyhow, well, that means we get alpha plus beta xi. Beta xi is the expected value of beta xi given that we know xi's value. And then we get the last term, the expected value of the error given the x value. Now, what we'll try to figure out is, we knew something about the errors. Now, sorry, it's not part of, I think you can still see this part of the screen, but if not, we assumed the errors had a mean 0. Thank you, Jenny. And so that seems relevant here. I mean, the expected value of the error, but is 0. This is the conditional expectation of the error. But we have assumed that the errors are independent of the x's. Because the errors are assumed independent of the x's, the expected value of the error given x value is the same as just the unconditional expected value of the error. And the unconditional expected value of the e's we assumed was 0. So this is the same as just the expected value of the error. And that is the same as, I'm just going to write that one in just so that we can make sure that's true. We wanted to figure out what is the expected value there given xi, because it appears in our equation. It's the same as the expected value of the error because the x's and the e's are independent. And the expected value of the errors is just assumed to be 0. So that is why we could figure out the answer to this first problem is our expected value of x, rather y given x value is just alpha plus beta xi. And that's certainly something we see written out in our applied econometrics text. But it's just, and sometimes maybe we might prove that, but I think usually not. But it's just an example here where then we can attempt to use the underlying assumptions in the model to establish or prove or show some things that might be familiar to it. So that was then the first problem that we have there in our notes for this section. And we have some others. Let's see, now we have plenty of them. And by the way, we'll be doing more fun next time with these. And the later ones will be using matrices as well, so some more tricks. And let's see, those we won't get to all of them just today, which is perfectly fine.
And here's one question.
Mhm.
If this was any number besides 0, we would have heteroscedasticity, right?
Oh, let's see now. Well, here, this term is the expected value of the error given the x. So if that were not equal to 0, then one of our assumptions would have to fail to hold in order for that to be non-zero. Now, if we had heteroscedasticity, we can have heteroscedasticity and still have, let's see, well, heteroscedasticity doesn't mean we can't have a mean of 0. So a mean of 0 is fine. Even if we put in heteroscedasticity, it doesn't invalidate that assumption. Heteroscedasticity could mean that the errors are, well, they could be actually dependent on x's. Conditional heteroscedasticity can make the errors dependent on x's in a special way. But let's see, I think, so we could have heteroscedasticity and it's not going to make this non-zero. And if it were non-zero, though, could we do that with heteroscedasticity? The simplest way of making this non-zero would be just to assume, let's say maybe the first half our population has a error mean of -1, and the other half of the population has an error mean of maybe +1, maybe. So if that were true, then that would just force this mean to be non-zero, or maybe the whole population just has a mean of 1. Even if we change the mean of this, though, it would, in principle, if all these errors had the same mean value, but it wasn't 0, we can actually just redefine the intercept in such a way that we could renormalize, if you will, the mean of the errors actually to be. So even though actually it is a special assumption that we have in the model, that the errors have a mean of 0, strangely, it's not actually quite necessary, because we could just reassign or reinterpret the value of the intercept to make the errors have a mean of 0. But there could be certainly ways that any of our assumptions in the model could be violated somehow. Maybe by heteroscedasticity, could certainly a way for some of our assumptions to be violated. And even though it is an important assumption that the mean is 0, it's not actually the most dangerous assumption, again, because actually it's just a certain measurement or kind of interpretation of the intercept and its units, if you will, in terms of whether or not the mean does have the mean of 0 for errors or not. So that's a very good question. Let me see if we can try at least one more of our problems today. Let's see.
I thought it was going to be the opposite answer. You proved that it could be a 0, but I thought the answer was going to be opposite in my mind. Yeah.
Oh.
Thank you for proving me wrong.
Well, we'll try to prove many things. Being wrong is not the one we're going to try to prove. Merely try to see if we can learn some new tricks and have fun and see if we can apply them in a useful way. Let's try number, let's see. Well, we'll just do the first. We can try the second one. And maybe the third one, because the second one's quick, and maybe the third one we can try as well. And by the way, so how do you like Professor Beshke's strategy? I mean, it's a possibility. Like if I were teaching in my office, I wouldn't have had these difficulties with the technology here in class. But because I surveyed these students before the semester, how are you feeling about online in the classroom?
I'm not happy about online because it's going to make the Zoom. I don't like the Zoom really because there's a lot of times when the professor speaks where it cuts out. You're right, or echoing.
Oh.
Yeah, like during the I don't know if it was my computer or not, but during the grad school orientation, I felt terrible because they were echoing. They don't even know they're echoing. You know, for me at least, I could hear echo. I don't know if everyone else could.
Okay. Yeah. But I'll try to keep my ears open about what what students would like come to your course this semester.
But I'll make your YouTube video real cool with introduction music. I'll put a picture of the SIU to begin with. I'll make it good for you.
Thank you.
You're welcome.
Let's see. We can find the expected value of the error given the axis. We already said, wait a minute, the errors are independent of the axis. So this is supposed to be 0. So we kind of actually showed this already, didn't we? We did. And we actually wrote 2 little steps for why that was true. Because this is the same as the expected value of the error by itself, and that's assumed to be 0 expectation. This has to be 0. So, while if we hadn't done that first one, we couldn't say we were done here yet. But I'm just going to put a check mark and say we actually showed this part in answering the first question. That means we could try at least one more of these for today. Show the OLS estimator can be written as a sentence. Straight ahead is the SXY or SX squared, where SXY is just the sample covariance between X and Y. And SX squared is the sample variance of X. Actually, that is not very difficult because, I erased our formula. But tell you what, 1 over n minus 1, sum of yi, and sorry guys on screen because I snuck this kind of small. But if I can do this, otherwise maybe I'll just rewrite it. It's a little too small. I realize.
You
Even for
you could
those-
put the other parentheses on the other side of the line.
You think?
Yeah, xi minus x bar.
You're right, but I think even then, because there'll be a
Yeah.
downstairs part of it, it might look
Yeah.
really horrible. So let me just write right down below that. Let me just write in the sample covariance between two variables x and y, and the sample variance, and I think if we cancel 2n minus 1 term, we get the beta hat.
Cool.
And then we have our sums, and we wrote earlier, we have xi minus x bar, yi minus y bar, xi minus x bar, squared, because that's actually the definition of sample covariance and sample variance. Those are our usual formulas. And we actually have different formulas for both of those even. And we sum of the xi, yi's minus, we have some ways of breaking out those terms, so on, but these would be our usual kind of definition formulas of those. And if we were then to cancel out the n minus 1 terms, we would just have our actual formula for beta hat that we solved for. And so sometimes it's useful to write a beta hat like this, because people that have seen an introductory statistics course, they know maybe perhaps they might remember what a sample covariance is. Maybe they remember what a sample variance is, and they say, well, beta hat's just the ratio of those two things. It does mathematically have extra terms in it, so maybe we prefer at some point when we're analyzing not to have the n minus 1 when we're kind of working with these as like formulas. But for interpretation at some point, it's maybe useful to have that. And maybe something to think about. How about we'll set up a problem that we'll work on next time, which is to derive the beta hat and the alpha hat. These are formulas that we can get from the OLS, ordinary least squares. Usually when I teach applied econometrics, I don't actually solve for the OLS estimators. We can do that though. We can solve for these, crank out the formulas, and soon we'll be getting to the OLS estimators in multiple regression with the great formula x prime x inverse x prime y, which generalizes what we'll see for this one. So let's just go ahead and set up the problem of deriving these beautiful estimators from the original formula, the problem that was set up by Gauss, the incomparable mathematician Gauss, Carl Friedrich Gauss, around 1800. He and Legendre, I think he assigned this, his teaching assistant, basically solved for these, but that was a problem they had considered a long time ago.
And they came up with normal distribution?
And that too, yes. Laplace and Gauss, a couple of the people that came up with a normal distribution or Gaussian distribution. Yes. So, question we were working on was 6. I'm just going to write it in a way that I'm going to say derive OLS. And so I'll use this term OLS because beta hat and alpha hat. These formulas are our ordinary least squares estimates. Alpha hat, OLS estimator of the intercept, population intercept alpha, and beta hat intercept slope estimates. We want to minimize. Well, let's see, for ordinary least squares, we minimize the sum of squared errors. And here we're thinking of, in a little bit of an abusive notation. Well, let's see, actually, maybe I'll use a little bit better notation. We're going to minimize over our possible choices, say A for what we put in for the alpha choice, B for the beta choice. We're going to minimize over that alpha plus beta x prime. if we minimize this, this squared difference is the squared residual when we try to predict y given our linear formula for z depends on x. So if we want to figure out what is a good, here, simple regression applied to the data, our least squares principle is can we minimize this sum of squares? Of course we can. We are powerful students in a graduate program. We have calculus and various other tricks. So has anyone derived the OLS estimators before? Oh, good. Something that we haven't done before. Oh.
This is
So
exciting.
long.
This is
Mhm.
exciting. I'm not gonna lie.
It's been so long since I've taken calculus. Can anybody have a hint? Any ideas how we could try to solve that problem? Minimize the sum of squares with respect to these two.
Let's do an integral, maybe?
Integral is possible. The calculus gives us integrals and it gives us derivatives.
Hamiltonian?
Hamiltonian could be, yes, possible. And,
Maybe using Lagrangian.
Lagrangian? Yes, so definitely something in there. Lagrangian often we use for optimization, and something that I think usually because we take a derivative at some point when we set up our Lagrangian. Take derivatives, set them equal to 0, find first order conditions. I think we can do first order conditions here. In fact, if we take the derivative with respect to A, set it equal to 0. With respect to B, set it equal to 0. Those are two first order conditions. And solve, and see if we can solve for what the A and the B values will be. I think what we'll find is we'll get a solution as long as the x's have some variation. If the x's are all 0, it's not going to work, or if the x's are just constant, it's not going to work. We do need to have some variation in the x's for our trick here to work, but as long as what we usually assume, we'll assume that the x's have a positive variance in our sample, then we will be able to solve for the A and B values. So we'll have our first order, just because I have limitations on my board real estate, I'm going to assume that these weird shorthands of FOC, no, actually FOC, first order conditions. Anybody seen that one maybe? First order condition. We want to take the derivative with respect to A, set it equal to 0, and with respect to B. So if I could just write in dA and then quotation mark, let's take the derivative of the sum of squares and set it equal to 0. I think the derivative of this is the derivative of the sum of terms. And I believe the derivative of a sum is the sum of the derivatives. So the derivative of this whole guy is the sum of the derivatives of each of the individual parts. And what is the derivative of a square? I think it's the derivative of x squared is 2x. Now we have a chain rule because inside here we have to do something. But if we use the chain rule, I think we'd have the sum of, so we have the sum of terms. Derivative of the squared thing is 2yi minus a plus bxi.
Times b?
And then, right, because we got the chain rule very good, then we got the chain rule part, but then we take the derivative with respect, take the derivative with respect to b, and with the thing that's multiplying b with xi. So if we just say, what's the derivative of bxi with respect to b? What would be xi? So we'd have xi. So I think, if I got that right, that should be the derivative of our sum squared with respect to, oh, no, so sorry. I think I was going to do with respect to a first, so sorry. Just one. Now wait, let's see, do I need also a minus sign, because it's minus. Okay. And I also forgot I already went to b, but we're only doing a. That's right, we got a minus sign, so it's derivative of minus a. Derivative of minus a is, with respect to a is minus 1 also. And what we would do is, and the point of taking the derivative is, if we do achieve a maximum, and it's a differentiable, smooth, objective function, we should have the derivative with respect to the a argument to be exactly 0. So that's the sense in which we have a first order condition. And we can try the second one. And then I'm just setting these up, and then next time we can go ahead and see how that works. We have 2 yi minus a plus bx I times minus xi. Equals 0. If I got that one right. We have two equations. We only have two unknowns. Hopefully we actually get a solution. We don't always get solutions. We have two equations and two unknowns, but as long as certain regularity conditions hold, or something happens that makes it work for us, then we will be able to solve. And next time we'll go ahead and try that. Give it a try yourself.
Will we
I see
use,
I ran over time even.
Will we use a matrix to solve this?
Yeah, no, we'll solve explicitly to get these, and then we'll go, by the way, we could have used matrices for this. And later next week too, we'll be making more extensive use of matrices. So sorry, actually, I went overtime instead of undertime, but we'll see you all
Oops.
on Thursday, either in classroom or online. Exactly.
Wonderful. We get a picture of the classroom.
I really appreciate it.